So we've kind of jogged your memory because we had a long weekend, and I figured you'd forgotten most of it, but it's come back to you. Yeah, Kyle, we're good? So I wrote down here, again, a thought experiment. Why would an athlete want low-mass shoes? And if you haven't noticed, over the past 15 years or so, the vast majority of the improvements in athletic endeavors have come from better equipment, not better humans. Some have. I mean, training is better, but most of it is actually from better equipment. So why would an athlete, like a track runner in particular, why would they want low-mass shoes? Pardon me? Okay. Newton's second law was the equation. See it there? F equals ma. Can you get the a by itself? Could you get the a by itself? So can you give me this? A equals what? Get the a by itself in that equation. If we have this, can you get the a by itself? I want the equation. You just keep saying math words. What's the equation? What over what? Hey, that's what I want. Okay? Now, let's suppose, we'll go back to Kai, a football player. Let's suppose that you have lifted weights, you have trained, and aside from performance-enhancing drugs, and this is going to be, you're going to see why Olympic athletes often cheat, you've maxed out naturally what you can, you've maxed out your force. What else do you have control of in terms of the force that your legs exert if you want your feet to accelerate faster? What happens if this number gets smaller? If you divide by a smaller number, what happens to your answer? So if you've maxed out the force, you've trained as big as you can, what can you control? Oh, I'll put a smaller m on the end of my feet. That's going to give me a bigger acceleration. As m decreases, a increases. Now we're going to go a little negative. Okay, so suppose you've maxed out, you've got the best equipment. Now what? Steroids. Change the F. Change the force that a human being is naturally capable of. This is Olympics, sadly, in a nutshell. This is the top track and field in a nutshell. Yeah?
So you're saying, no, why aren't they always running without shoes?
Why aren't they running without shoes? Some they do. So you guys are too young to remember back in the 80s, there was a female marathon runner from South Africa who ran in bare feet and did quite well, and it was Zola Budd. The issue is going to be what you can't afford is that they cut their foot. You have to protect their foot. But I guarantee if you actually looked at like Usain Bolt's pair of sneakers and you picked it up, you would almost, it would almost feel like it was weighing nothing. I'm willing to bet it's probably a $500 or $600 or more pair of sneakers, and the mass is probably pretty impressive. Also, because we talked last day, when you're walking or running, what force is pushing you forwards? It's not your feet. What force is pushing you forwards? Because your feet are pushing backwards. What force did we say is pushing you forwards? Begins with the letter F. Friction. Oh, you know what, Josh? I can add tread to the bottom of my sneakers and increase friction. I can control that too. Okay, so we've thought of that. Good question. A force with which you have had some experience is the force of gravity between you and the earth. This force is also known as weight, and weight is measured in newtons in the SI system, or in the imperial system is measured in pounds. Pounds is a measure of force, not mass. Force of gravity is not the same thing as mass, although they are related. Mass is the amount of matter in an object. Really, it's how many atoms there are in there, add them all up. Measured in kilograms, or slugs in the old system. To relate mass to force, we need to know the number of newtons of force per kilogram of matter, what you called the acceleration due to gravity. Or often we just used a lowercase g last year. This quantity is known as the gravitational field strength. Near the Earth's surface, the gravitational field strength is 9.8. Oh, and Clay, if you want to use the gravitational field strength as an acceleration, instead of saying 9.8 newtons per kilogram, you'd said negative 9.8 meters per second squared. But the reason it's a 9.8 meters per second squared, negative, is because the acceleration, the gravitational field strength is 9.8 newtons per kilogram. The moon's gravity field is about 1.6 newtons per kilogram. Or again, Jason, if you dropped something on the moon, it would fall at about negative 1.6 meters per second squared. You guys used this last year quite a bit. You said Fg equals m, and you used a lowercase g to symbolize the acceleration due to gravity. So if I want to find the weight of a 10-kilogram object on the Earth and on the moon, will they have the same mass? Yes. Will they have the same weight, the same force of gravity? No. For both of them, it's going to be right? Except it's going to be g on the Earth and g on the moon. What mass are we talking about? 10. What's the gravitational field strength on the Earth? 9.8. Please don't reach for your calculator. Please tell me you can go 10 times 9.8 in your head, please. 98 newtons. Compare that with on the moon. That object would still have a mass of 10, but what's the gravitational field strength on the moon? I don't know. If I was clever, I would have highlighted it in blue in the previous paragraph. 1.6? Really? How'd you figure that out there, Raj? Oh, it says there? Cool. Excellent. We missed you. In your head, 10 times 1.6, Spencer, is what? Good. So again, let me emphasize, and this is why, Kiowa, my earlier outer space example, in outer space, the weight would be 0 newtons, but it would still have mass, it would still have inertia, it would still hurt if it hit your face. Or another good question is, could you have a fist fight in 0G? Yes, and it would still hurt. The only issue is when you hit the first punch, you'd also end up drifting backwards. You'd have to be tethered to something or somehow be able to stabilize yourself. And that's really a lot of the issues with working in outer space. As an example, using a power drill in outer space, if you don't have your feet tethered to something, well, if the drill applies a force, if you apply a force to the screw this way, the screw is going to apply a force to you in the opposite direction, and you'll start spinning. Okay? That's why they do so much underwater training, that big pool that they have in NASA, because underwater can mimic 0G. If we put a neutrally buoyant suit on you pretty good, you can at least learn, oh yeah, I gotta remember that things will float away on me if I don't tether them down. Example 3. Oh yeah, turn the page. Example 3 says, select the best answer. If the force of gravity acts on an object, then the object A remains at rest, B moves at a constant speed, C accelerates in the direction of the force, D, all of the above. Once again, we're going to vote. How high you hold your hand up is how sure you are of the answer. I'm positive. I'm pretty sure. I'm only voting because Mr. Dueck will make fun of me if I don't vote because he wants me to have an opinion. I'm positive. I'm pretty sure. Don't hurt me, Mr. Dueck. Okay. So, if the force of gravity acts on an object, then the object, who says answer's got to be A, Mr. Dueck? The object remains at rest. 0. Who says, Dueck, it moves at a constant speed? B. 1. Who's, Dueck, it's gravity. It accelerates in the direction of the force. 1, 2, 3, 4, 5. Who says D, all of the above? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Hey, the math works. It is everybody. So, Then I always pause and I say, you can either attack or defend. You can attack someone else's answer as that has to be wrong, or you can defend your own answer as that has to be right. Convince me. Whichever one you voted.
You can remain at rest because right now we're just sitting here and gravity's pulling on us. We're not going anywhere.
Okay, you know what? So first of all, what did you vote?
D.
D. So D is correct. How can you remain at rest? Is gravity acting on you right now? Are you accelerating right now? Okay, so you know what? I'm going to go like this. In my answer, I'm going to go A, sitting at a desk is a great example that A can be right. Can you give me a way that B could be right, that gravity could be acting on me, but I'm also moving at a constant speed?
Free fall.
What about free fall?
When you're falling and air resistance is holding you at the same speed.
So when I jumped out of an airplane, eventually I jumped out of an airplane. When I jumped out of an airplane, eventually I did hit terminal velocity. Yes? And that's the phrase I'm going to use. Terminal velocity in free fall. What that means, normally we ignore air resistance, but in real life there is air resistance. Eventually you're going so fast that air resistance is canceling out the force of gravity and you're at a constant speed. A terminal speed, because if I hit the ground at that speed I will die, but a constant speed. Can you give me an example of how C could be correct? How about free fall in a vacuum? I can never, is that how you spell vacuum? 1 C, 2 U's? I don't know. I got 2 U's in there. Is it 2 C's or 1 C? I don't think it's 2 C's. No, it's 1 C. I was right. Never listen to my students again. So Clay, since A is correct and B is correct and C is correct, what's your conclusion? What's the correct answer?
D. Because it's all.
Therefore, D. That would be, you know what? I would give you full marks for that explanation. I'd figure out what you're getting at. Okay. Gravity is acting on all of you right now, but you're not accelerating. There's situation A. And I love the way Clay handled it. He said, look, I'm not sure that it's all of the above, but if I can find a situation that applies to more than one, it must be all of the above. That's good test writing or good thinking. Have I convinced you okay? So, Newton's first law says, if we have balanced forces, then objects at rest remain at rest and objects at motion remain at motion. If we have unbalanced, and the fancy word for unbalanced, Travis, is net forces, then the object accelerates in the direction of the net force. F net, or has anybody seen this symbol right here before? Does anybody know what that means, that little funky E? Okay, it means the sum of, or if you really want to, in one word, total. The total force, if you add them all up, and since force is a vector, it means you would have to add them all up vectorially, tip to tip. If you add them all up, that's the net force. Oh, and if you add them all up and everything cancels, I'm telling you, you're not accelerating. You're either at rest, or you're moving in a straight line at a steady speed. Outer space. Okay. Isn't this one Einstein's? Which one? This? This is Newton's equation. Einstein's is going to get, are we going to get into relativity this year? One of the ones that, so first of all, Brandon, all of this under Einstein is wrong, okay? As soon as you start approaching speeds close to light, a lot of this breaks down. We're not going to do that much this year because we don't have the equipment to do it. Einstein's, his famous equation is the E equals mc squared, I think, if that's the one you're thinking about. Yeah. There's others that he's famous for. Oh, nerd note. Remember, back here, I said that the gravitational field was 9.8. But look what units I used, newtons per kilogram. But last year, whenever you wrote 9.8, what units did you call that? Meters per second squared. Are those the same? Well, Raj, it turns out, yeah, newtons per kilogram is the same as meters per second squared. And I'll do a little convince you. Newton's force is ma per kilogram. Newtons per kilogram is mass, sorry, meters per second. Let me do this again. M, and yeah, let's do it this way, Mr. Dueck. This is the same as MA over mass. Newtons is MA, kilograms is mass, and you're left with meters per second squared. So another term for acceleration due to gravity is gravitational field strength, measured in newtons per kilogram. Pause the video for 1 second. So let's do a few. We're going to be using a skill or a trick. Kyle, are you going to make it? You're looking a little dead there. Okay, he's alive. One of the things we're going to be doing an awful lot in the forces unit are what we call free body diagrams, or FBDs. This is kind of an introduction to them. It says this: find the net or the unbalanced or the resultant force for each object. Let me zoom in. Kai, was that big enough? Because you're the furthest away. You can see that okay? Yep. Yeah, okay. What's the net force on object A? Magnitude and direction. And you know what? Let's do this. North, east, south, west. Let's put a compass rose on here. So now we have a direction. I'm going to go at east so that you can tell it's a direction. The reason I do that is if I went 2 newtons north, that's really confusing. So I always put an at if I'm going to do a direction. You don't have to, but let's be organized. Okay, what's the net force here? B.
3.7.
So if they're in a straight line, pointing in the same direction, just like last year, we can add them up. 3.7 newtons at direction south. What's the net force here? Direction? 1 newton north. And the phrase that I use here, and you're going to hear me say this quite often, is you're doing vector mathematics, but really you're going winner minus loser. You're saying, what's the biggest one? That's the direction, and then I'll just go biggest minus smaller. Or if they're in the same direction, I'll just go biggest plus smaller. Let's get a little more complicated. D. E. Now, vertically, or north-south, the net force is what in the north-south direction? 0. And this is what I meant. Newton's first law says, look, if you're not accelerating, you can't assume there's no forces. What you can assume is everything is canceling out. There might be no forces, but at least you could assume everything's canceling out. Horizontally, what did you guys say it was? It was 7. 7 direction? Did anybody go -12 plus 5? Or were you all clever enough to say, you know what, it's going to be easier just for this question to let left be positive because it makes the math nicer. We're going to do that fairly often. We're going to let the positive direction be whatever makes the math more convenient. And then we'll just decide to be consistent. So if I was doing this, I would have just said, you know what, I'm going to let west be positive, and it's 12 take away 5, instead of going -12 plus 5, because then I got to do yucky math. Algebraically, what? Sorry, hang on. What was that? That's why I said y is greater than x, and I tried to draw it longer. So mathematically, what would you do here? So I'm going to go in brackets, y take away x newtons, but I can tell you the direction. What would the direction have to be? Which way must this object be accelerating then? It has to be. That's Newton's first. And that's the power of Newton's first law. It says, look, if you've listed all the forces, you can figure out which way this thing is accelerating. Mr. Dueck, yeah? What if we had one force this way and one force that way? Tip to tail? If we needed to, although you're going to find we'll often just stay in components. Mr. Dueck, what if we had a slanty force? Did I say slanty? We're going to break it into components. Question? You're good? So, to solve force problems, to solve projectile problems, T-table. AX equals 0, AY equals negative 9.8. Oh, is the velocity at an angle? Components. Okay, I'm trying to build habits. To solve a force problem, 99% of the time, the first thing I'm going to do is a good free body diagram, or the abbreviation for that is FBD. To draw a free body diagram, what you do is you represent the mass with a dot, and then you label the forces on it with arrows, roughly to scale. So if I was recreating the diagram on the left, I would go, okay, mg, gravity. It looks like that block is sitting on a table. Is that block sinking into the ground like quicksand? Is it flying into the air like Superman? Then I must draw exactly the same length as mg. There must be an identical force, same magnitude, pointing up. That's what we call the normal force in this case. And then it looks like there's an unbalanced force that way called force F. If you saw that diagram, based on Newton's first law, which way must this object be accelerating? To the right. To the right. Okay? It has to be. Then if you want to add more stuff, and those of you that have had me before know I tend not to put extra stuff on my free body diagram, but if you wanted to do like an acceleration, you could maybe do that with like a wiggly line or a dotted line or something. I tend to keep, excuse me, Max, I tend to keep my free body diagrams pristine. I put the forces on there and nothing else. Once you have your free body diagram, you write a net force equation like we did right here. Our net force equation will be derived using a tug of war analogy. I'm going to ask myself, which force is winning? And I can almost always figure that out. And then rather than letting up be positive and down be negative, or right be positive and left be negative, please trust me when I say I'm going to go like this. Winner, take away loser equals the net force. I'm always going to let whichever force is winning be positive. It makes the math so much easier. You don't have to do it my way. Do it my way. You don't have to do it my way. Do it my way. You can do it your own way, but please trust me that I've done this for a while. That does mean that if I know it's accelerating downwards, if gravity is the winning force, I'll let down be positive. The math's going to be nicer. Okay? Oh, and then what is it always going to equal? It's going to be winner minus loser equals F net, except, put a little comma here. F net is always going to be MA. So really my equation is going to end up being this. Winner minus loser equals MA. And I'm going to try and teach my brain to go fairly systematically on these. And you'll figure out what I mean in a bit. Example 5. Based with this, I can already start to solve stuff. It says this, a 2,000 Newton rock hanging from a rope accelerates upwards at 3 meters per second squared. A says, draw a free body diagram. Okay, I'm going to represent the rock with a dot. What are the forces acting on this rock? Get the obvious one first. Gravity. And I'm always, you're going to hear me say that every time, because this is my whole, you know, if you write something down, you feel better and you're not as stressed. Gravity. And which way is gravity acting? downwards. I'm going to go like this. Yoink. FG. Is this rock in free fall? Then there must be another force. In fact, which way is this rock accelerating according to the question? Read the question. Which way is this rock accelerating? All of you underline the word upwards. In your homework, you don't have to, but in our notes, we will. You know what that means? It means the winning force must be upwards. The net force must be upwards. What that means is I'm missing a force. What direction will I point that force? Up. Will I draw the arrow bigger, smaller, or the same size as gravity? And I'll exaggerate it. What force is that? Well, now I look at the picture. What could be pulling this rock up? The rope. What did we say that we were going to call the rope force so that all of our notation looks consistent? I'll give you a hint. Some of you are feeling it because there's a test coming up. Tension. Tension. There is my free body diagram. I know it's accelerating up, Alex, therefore there must be a bigger force pointing up, but I started out, get the obvious one, gravity, because I feel better, I got it. Who's winning? Tension. Who's losing? Who's winning? Who's losing? Okay. Part A said, done. B says, compare the forces. We did that when we drew it. It's obvious which one is bigger. We figured that out because upwards. C says, write a net force equation. Okay. Part C, well, it's going to be winner take away loser equals MA. Look at my picture, my free body diagram. Who's winning? Who's losing? There's C. What does D want me to find? Oh, do I have tension in this here equation? How would I get the T by itself? How could I move this over? Plus it? So if I hear you correctly, Spencer, and I think I do, you're saying tension is going to be MA plus MG? Yep. Some of you will be tempted to go to this line in your head. I'm going to say resist the temptation. Draw the free body diagram, derive the equation. It takes about 2 seconds, but it's great practice, and it's good bang for your buck. And the biggest mistake is kids have these flip. They want to go MG minus MA or MA. It prevents it. Uh-oh. Did they tell me the mass? 2,000 is the mass? If that was the mass, what would the units be next to the 2,000? Kilograms. Are there kilograms there? So I'll ask my question again. Did they tell me the mass? What is that 2,000? The weight. Another word for weight is? Not mass. If it was mass, it'd be kilograms. Jason. Okay, so you know what? The FG is going to be plus 2,000. I don't know why I put brackets there. I didn't need to. And, hey, what's A? Oh, did they give me an acceleration in the question? 3. If I know the force of gravity is 2,000 newtons, who remembers from last year, how can I use that to find the mass? I heard someone, I think I heard it. Divided by 9.8. So you know what? I'm going to be clever, Manny. I'm actually going to write over here 2,000 over 9.8. I could do it on a separate line, but why not just do it in my calculation? I've got a good calculator. Hopefully my physics teacher went on a bit of a rant at the beginning of the year about the usefulness of having a decent calculator. Hopefully by now some of you have taken his advice. M, which is always the weight divided by gravity. A plus force of gravity. What's the tension in the cable going to be? M, 2,000 divided by 9.8 times 3 plus, I think that'll work. I might need brackets, but I think on my calculator this will work. Double check me. Do you guys get 2,612.24489? That? How many? Is that a final answer? Yeah? How many sig figs do I want to go to? 3, which is that 1 right there. Will that 1 stay a 1 or become a 2? And I guess I'll just put a 0 on the end. I'm going to write 2,610 newtons. Touchdown. And you see, Alex, with Newton's laws, a free body diagram, we were able to solve what otherwise might have been a fairly tough question by just going systematically. Example 6. Once again, you're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. Is it correct to say that if the rock in example 5 is moving upwards, then the string tension must always be greater than the weight of the rock? True or false?
False.
Okay. So here's the question. We're going to vote without blurting out an answer.
Sorry.
Is it correct to say that if the rock in example 5 is moving upwards, then the string tension must always be greater than the weight of the rock? Certainly it was in our example. Who says true? 3, 4, 5, 6, 7. Oh, now all the basketball guys go 8, 9. Who says false? 3, 4, 5, 6, 7, 8, 9. A bunch of you didn't vote. Convince me.
There could be a pulley outside the diagram or a snatch block.
Still the same. I'm not sure that would change the string tension necessarily.
But then how does it, if you're pulling a vehicle with a winch and you put a snatch block, you have 8,000 pound line, but you're pulling a 16,000 pound load. It doubles your pulling strength.
It transfers some of the force to the pulley itself. Well, let me come back to that. There's without changing or adding equipment, it is possible to answer this question. Okay? You had a hand? No?
The weight of the rock is the FG, and if the string tension was smaller than the FG, the rock would come down.
But it's moving upwards. Question specifically says. I'll do that even, because that is the answer. Can someone think of a way that we could be moving upwards? If the acceleration equals Nope, don't need that in the question. Oh, I thought I heard somebody say, what did you say, Spence? What if your acceleration is 0 but you're moving up? Is that possible? Well, yeah, we would just say you're moving up. If your acceleration is 0, you're moving up at a constant speed. What would that look like? Well, if we look at our equation, which was tension equals ma plus mg, if A was 0, what would happen to this right here? Right? And therefore, tension would equal mg. If you equal mg, are you greater than mg? So there, I've just given you, you know what? If it's going up at a constant speed, tension doesn't need to be greater than mg. It can be equal. Okay. For a rock moving upwards, is it ever possible for the cord tension to be less than mg, the weight? So I've just given you an example if A is 0 where it's equal. Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. So the question says, for a rock moving upwards, is it ever possible for the cord tension to be less than the weight? And remember, the weight is a synonym for mg, the force of gravity. Who says yes? Who says no? Now, I'll let you think about a way to do it. I'll pause. Okay? Now, there's a fine line because I've also told you if that mass was heavier, I could yank the rope so hard that the rope would snap. True. But certainly, I've also showed you that I can yank it hard enough to put slack in the rope. It'll keep going up for a while. It was going up. Not the whole time because it started to fall back down, but it was going up, and you saw slack in the rope. Now, I love these two examples. I'm not saying I like this question, like this question, like this one. The reason I like these two is hopefully what I'm teaching you when I give you a thought problem, go to the extremes. What if A is 0? What if A is, always go out to the extremes. That's often where you're going to find the answer to a true or false question. What if the force is maximum? What if the force is minimum? Or if we're talking about slopes of roofs, what if the roof is vertical? What if the roof is flat? That might help me wrap my brain around what's going on, that kind of thing. Oh yeah, good. A technical comment on force equations and vectors. If the mass that we just did in example 5, that rock, was accelerating down, say at 2 meters per second squared, we have two choices. We could use the sign convention from the previous unit. We could say let up be positive, down be negative. And therefore we would say tension minus mg equals m negative 2. That gives us negatives kicking around all over the place and yucky math. Or, this is what I prefer, we could just decide, hey, which way is this accelerating? That's the winning direction. That's going to be positive. For the rock, since it's accelerating down, the net force is down. That's the winner. Therefore, I would let gravity be positive. I would go mg minus tension equals ma, and I would just recognize that my direction is down. That first approach, approach A, works great for one-dimensional problems, but what about for something like this when we have two-body problems? This mass is accelerating down, negative. This mass is accelerating right, positive. Mr. Dueck, I don't know. You know what? We're going to break away from that. We're going to decide who the winner is, and that's going to be what direction it's accelerating. Okay? We'll finish with this. Sorry for those of you on YouTube, you're wondering what the tricycle demonstration is. Sign up for my class. Anyways, what's your homework? Folks, your homework is to prepare and study for your test. However, after your test, I see you a week from today. You can try number 1 by then, number 2 by then, number 3 by then. Number 4 by then. 5 is good. I'll pass 6 just to annoy Clay. 7 is good. Folks, every year kids way overcomplicate this. First of all, what's number 7 saying? Find the? What's another phrase or expression for weight? What's weight a synonym for? The force of gravity. Now, on the Earth, you can do that. What about on the moon, Mr. Dueck? I need to know G on the moon. Spencer, did I give you G on the moon in the notes earlier? Yes. I did. The 1 point, I think it's 1.6. It's in your notes. It is. Okay. Right now, I've assigned 1, 2, 3, 4, 5. Skip 6, 7, Skip 8. 9, and 9 gets a star because it's fairly nasty. Okay. Well, no, that tells you, oh, this will be an idea of a question that Mr. Dueck might put as a fairly tricky multiple choice curveball-y kind of a question. If you see number 9 right, it's actually all physics 11. The trick is to see it all right. There is, I tried to give you 15 minutes. That's actually also yours to work on the ultimate kinematics review, to study, to work on stuff. Let me just hit pause.